Alright, so by this time you should have watched a few videos on the Big Bang and maybe even done a lecture tutorial on the Big Bang. So here's a couple of clicker questions. Hopefully you can answer by now and look for those on Moodle. What best describes the Big Bang? There's a few choices. Or is it more than one of the above? That's from the lecture tutorial. Here's another one. If you watch the history of the universe playing backward, what would you see? This is a good one to answer after you've done that lecture tutorial. All right. So, following on section 29.1, there's a couple of other ideas that help us to understand the Big Bang and kind of what's going on. Kind of tangential ideas, but important ones. The first of those is look back time. So, look back time is this idea that the farther we look in distance, the farther we look in time. And it's based on the idea that we have seen before that the speed of light is finite, that light takes time to travel, and so the time light takes to travel from a distant object, light takes to travel, is called the look-back time. Time light takes to travel from a distant object. Even our sun, which isn't that far away, has a look-back time of about 8 minutes, because light takes about 8 minutes to travel the 93 million miles from the sun to us. So we're seeing the light as it was 8 minutes ago. Closest stars, about 4 years. And of course, galaxies, to think about the entire universe, billions of years. So that's sort of the context here with the Big Bang and expansion of the universe, is that distant galaxies have a very large look-back time. Okay? If they are 1 billion light years away, then we're looking back 1 billion years. Have a very large look back time. And the consequence is that when we look at galaxies that are distant, we can learn something about what was going on in the early universe. Because we see them. We see these distant galaxies as they were in the past. Okay, as they were in the past. So this idea links what we're learning about the Big Bang with what we learned about galaxy formation and structure formation. How do we know what the early universe looked like? Because when we look as far as we can with the Hubble Space Telescope and other instruments, we are looking into the past, and that helps us to know how these things formed and what things look like right after the Big Bang. So, in other words, we can learn about the early universe just by looking farther away. Okay, we can learn about the early universe by studying the most distant objects. They're some of the hardest things to study because they are so far away. They are very, very dim, and we need special tools to see them. We hopefully will launch the James Webb Telescope, which will help us a little bit with that. But the idea is here that as we look back in time, we can begin to understand what was happening. How did those first stars and galaxies form? We can't see all the way back to the Big Bang. We can get kind of close, and we'll talk about what we can see. But this is how we know. This is where we get this observational evidence for all of these theories that we have been talking about. It's kind of a weird thing, too, to think that we're seeing things in the past and not as they presently are. We don't know what those early galaxies look like today. We have to wait billions of years before we can see them, before the light from them gets to us. So speaking of that, light traveling over these large distances, we're going to clarify something a little bit, give a little bit more detail about something called cosmological redshift. And I didn't change my numbering here, but cosmological redshift is actually in section 29.2 rather than 29.1. So we talked about redshifts. Y'all remember redshifts? We said if something is moving away from us, its light's going to be shifted to the red, those absorption lines shifted. Okay, well, here's a little clarification now that we know about the expansion of the universe. Redshifts of galaxies aren't exactly normal Doppler shifts. So let me explain. Let me write this down. So redshifts of galaxies are not due, are not due to normal Doppler shifts. A normal Doppler shift is that train passing you, that siren passing you, something moving past you, right? Because if you remember, think about our rubber band paper clips one more time. Think about the everywhere stretch, not the Big Bang. That those galaxies aren't flying through space. Instead, space is stretching. So look at the picture here. So a Doppler shift would say that this star is moving away from us, towards us. Expansion says, actually, we're both moving away from one another because the rubber band is stretching. So we're taking that blue light and we're stretching it into red light because the universe itself is stretching. So that's the clarification I want to make. So let me just write that in different words, okay? So galaxies don't move through space, but with it, right? The paper clips. They don't move through space, but they move with space as it expands. Okay? But with it as it expands. And that's actually what causes the redshifts, moving with space. The light becomes stretched out. And so we can use, here's our rubber band, and we took the paper clips off. This time, we think about stretching out the waves. You can also think about this in terms of the balloon analogy. Hopefully you've watched that video by now too. That the idea is that the light itself, those light waves, are stretched out. So the light is stretched out with space as it expands, okay? With space. Remember, the light is traveling through space. Remember, it took billions of years from the light to get to us from the distant galaxy because of the large look-back time. So it's stretched out with space as it travels through the expanding universe, okay? As the light travels through an expanding universe. Again, this takes a little bit of interesting thinking to get this idea through the expanding universe. Imagine that galaxy with a large look-back time started out and sent out some blue light. But over the 13 billion years that it's taken for that light to reach our eyes here on Earth, the universe has expanded. And as space-time expands, the light wave stretches out. Because look at the grid gets bigger, and so what used to look like blue light looks now like red light. That is cosmological redshift, not exactly the Doppler shift, not galaxies flying through space, but space itself stretching. Alright, watch those videos, do the lecture tutorial and the clickers. See you later.